Hi everyone. So in this video, I will talk about pressure distribution and hydrostatic force on submerged surfaces. So let us see on the diagrams that are shown on the slide. So the diagrams show a tank that is filled with fluid. So the fluid will exert pressure onto the surface of the tank at the sides and also at the bottom. So at the bottom of the tank, the pressure is distributed equally. This is because the tank is flat, it is on the same horizontal plane and it is not at an inclined angle. Therefore, pressure is distributed equally. So the force or the pressure force is concentrated at the centroid of the bottom of the tank. So this force is called as hydrostatic force. You can use Fr or Fh to denote the hydrostatic force. Hydro means water and static means stationary or at rest. So normally the fluid that is used is water. Therefore, hydro is used. So hydrostatic force. And at the sides of the tank, you can see that pressure is not distributed equally. This is because the side of the tank, the depth increases. So pressure increases with depth. So the pressure at the surface of the liquid or the fluid is due to atmospheric pressure. So if we consider gauge, it's 0 and it increases as the depth increases. Pressure is the maximum at the bottom of the tank. Therefore, the force is not concentrated at the centroid of the side of the tank. So let's say we consider this is at the centroid of the tank. So the pressure or the force is acting slightly below. The force is perpendicular to the plane surface. So the line of action or the force or the point where the force is concentrated is called as center of pressure or CP. Alright, so how do you determine this force? So let me introduce to you the magnitude of hydrostatic force. So before that, we need to derive the equation. So let's say we have a plane surface of any arbitrary shape. So it can be rectangle, it can be circle. So this plane surface is submerged in a fluid. So let's say this is the fluid. For example, it's water. So let's say it is also inclined at a certain angle. Okay, so let's say this is a reference point O, and we consider this as our y-axis, and we consider this as our x-axis. So if we consider a certain depth on an elemental area dA, so the force acting on this small area dA is dF. So dF force is pressure times area. So why we need to use differential equation? Because the pressure is not distributed equally. Okay, and let's say this is the centroid of the plane surface. So force equals to pressure times area. So pressure, as we know, is rho GH. The rho is the density of the fluid, G is the gravitational acceleration, and H is basically the height or vertical height from the water surface to the line of action of the force. And we know that if we draw a if this is y-axis, okay, if this is y-axis, therefore the inclined distance from the water surface to the line of action of the force is called as y. If we draw a triangle, you should get a relationship between h and y, a certain angle here. So basically sine theta is h divided by y. So therefore, this can also be written as y sine theta. Alright, to get f, I integrate. So I integrate both sides. So I will get sine theta. I put the constant first. So y dA, I integrate both sides. So this term is called as first moment of area. So the first moment of area, okay, about x-axis. First moment of area about x-axis. And it's equal to the whole area, times with the distance, okay, the distance from centroid to a reference line. So the reference line is the x-axis. Okay, so distance from centroid to x-axis to a reference line, where the reference line in this case is the x-axis, to a reference line. Therefore, the whole area is area. So the distance from the centroid to a reference line, I call it as centroid. So centroid to the reference line, I call it as y. Okay, yc. So I replace in this equation. Therefore, f, after I integrate it, I get sine theta yc times with area from the first moment of area about x-axis. Therefore, rho g yc sine theta area. So yc sine theta, if you go back to the slide here, to the diagram here, so yc is related to h, this vertical distance from the water surface or the fluid surface to the centroid. We call it as hc. Yc because from it is the distance from the water surface or fluid surface to the centroid. That's why it is called hc and yc. So if we draw the triangle relating the hc and yc, you will still get the same triangle with an angle of theta. Therefore, sine theta is also equal to hc divided by yc. So therefore, yc sine theta can be replaced with hca, or it is also can be written as gamma hca. So this should be the magnitude of hydrostatic force on a plane surface. Alright. However, even though the magnitude is determined by using hc, where hc is the vertical distance from the water surface to the centroid of the plane surface. However, the force is not acting at the centroid. It is acting slightly lower than the centroid due to the pressure variation. So it must be through CP, or center of pressure. So therefore, to find the exact location, let us derive another equation. So we fill in again. This is HC, this is H, this is the force. So the force just now is hydrostatic force or resultant force. Resultant force. So this again is YC, this is angle, this is reference point, this is Y axis, and this is X axis. Another thing just now is this one. This is Y. And this is Y. So remember that just now the force, I put it as FH or FR, resultant force. It's equal to, just now it's equal to, what just now, rho G sine theta. So before we integrate just now, it is this, right? Before we integrate, okay. So if I want to find the exact location of this force, so I need to know I need to do the summation of moment about reference point. The reference point is O. To do the moment, force must times with the distance, perpendicular distance. Okay, so let's say I put this as Y resultant as well. Y resultant. Okay, I times with the force with Y resultant. The resultant force times resultant distance from point O. So on the right side, I also need to times with another Y here. Okay, so therefore, this term, okay, just now is the first moment of area. Okay, now it is the second moment of area. Okay, so now it is the second moment of area, or also called as moment of inertia. Moment of inertia. All right. Moment of inertia about x-axis. Okay, about x-axis. So we call it as Ix. So in other words, Ix. Okay, so Ix is a measure of how resistant a shape, how resistant a shape is to bending. In other words, it is called as the strength of a shape against bending, and is given by Ixc plus Yc square A. Alright, so basically Ixc is the moment of inertia of a body with respect to x-axis that passes through centroid. So that's why it has x and c. X and c. Okay, moment of inertia of a body with respect to x-axis that passes through the centroid. Alright, so if I rewrite this, yr is equal to rho g sine theta moment of inertia dA. You divide with Fr. Okay. Fr from the previous slide, Fr is basically rho g and theta. So this one you just replace with Ixc plus yc squared a. So Fr from the previous slide, it is rho g sine theta yca. So this one cancel. Okay. So you can see that what you get here is Ixc divided by yca plus yc. So you get yc. Okay. So you go to the diagram. So yr is equal to yc plus, so this term, okay, so we have yr here, yc, then we have another distance here. So this distance is where it is from the centroid to the line of action of the force. From the centroid to the line of action of the force. We are call it as ycp. Why I call it as ycp? Because it's the distance from the centroid to the cp. This is cp. Okay. So basically, this is ycp plus yc. So normally, to find the location of the hydrostatic force, you need to find ycp and yc. Alright. So I hope that helps you to understand the hydrostatic force on submerged surfaces. If you have any question, you can ask me. So later, I will make another video on hydrostatic force on curved surface. Alright, thank you.